Okay, so today we'll talk about recursive algorithms. And one of the strange things about teaching a course like Java is that towards the end of the course, you've given out the assignments and enough time to do them. So you have this extra time where there are lectures to be given, but you're not going to actually implement any of that in the course itself. So it's kind of a strange thing. So I throw on these extra topics like sorting and searching and recursive algorithms just to give you some introduction to the topics. Might be useful for coding later on, but I don't get into it enough to actually give you assignments that really use it very much, although one of the lab exercises did. Anyway, a recursive algorithm is a method that calls itself. So we'll introduce some of this here. Anyway, the standard way they set up these chapters, after you've read and studied this chapter, you should be able to write some recursive algorithms, understand when and when not to use recursion, and talk about the recursive quicksort algorithm. So quicksort, if you were here the other day when we talked about searching and sorting, I mentioned that there is a quicksort algorithm that in some ways is better than heap sort that we did, and in other ways not. So we'll talk about that one a little bit. All right, so one method that's easy to bring up as a recursion is a factorial. All right, now there's a couple of simple ways you could do factorial. So I'll set up some files here. I'll call it fun with recursion. So you all remember what factorial numbers are. So we'll make one, return a long loop factorial, and accepts an int n. Okay. Now, if I wanted to do a loop factorial, the simple way I would do it is I would start with some number equals 1, and then as long as I need to keep multiplying it by the next number up, I do. So let's see, int result equals 1, right? And then down below, return the result. And in between, I have a loop. So if the n is an integer greater than 1, I multiply it through every number. So I can do for int equals 1, do it as long as I is less than or equal to n I plus plus. Okay, and then for each one of those, I simply say result times equals I, right? Result times equals I. That's right. So I could do something simple like that. I could call, let's see, fun with recursion FWR new FWR dot loop factorial. Now let's suppose I want to find the number 10 factorial. Okay, suppose I didn't know what that was and I want to do it. So let's print that out. Run that, and boom, I get this old familiar number. Looks like it could have been a phone number back in the day. Okay, so very simple, right? I can make up a loop that does, and if if you're wondering, hey, I don't even know if that's true, I could do a simple one like 4 factorial, which is going to be 2 times 3 times 4, which is just 24. Verify if that works. Ta-da, 4 factorial is 24. Okay, so it's easy to do with the loop. However, if I wanted to, I could do a recursive version of the same thing. All right, so long recursive factorial, where I call the method itself. And I'm just going to borrow the code they have here in the slides. So slide this over so I can see it. So again, we remember I have to multiply n by n minus 1 by so on. So to set up this as a recursive method, here I return an int. I say if n equals 1, return 1. Otherwise, return n times factorial of n minus 1. Right? So this I'm going to basically put in the Eclipse, but I'm going to adjust it a little bit. So there's a lot of these garbage characters that wander in with the slides. Okay, so I'm going to make you n, 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 and then go recursive. Okay. And if I wanted to get rid of these braces too, I guess I can do that. So it looks a little simpler. I'll leave that. So I could do this. I could say if n is 1, return 1, otherwise return n itself times the recursive of the next lower one. And this will do the same thing. For example, if I do likewise, 5 factorial is fwr.recursive factorial of 5. Okay, and that's going to be 24 times 5 is 120. So again, let's run this, make sure I implemented it correctly. Boom, there we have it. Okay, so what can we say about this? Well, in this case, the recursive algorithm isn't much more than an interesting bar trick. There doesn't seem to be any clear advantage. You know, it doesn't take, it takes like 1 line less of code. Okay, that's nice, but it's not that huge of a savings. And it's a little weirder to understand, right? I think most people, maybe I'm wrong, most people would look at this, they understand instantly how the loop factorial works. With a little bit of thought, they can understand how the recursion works too. But, you know, it's not something that people say, oh, wow, yeah, of course you're going to do it recursively. That's, you know, the only sensible way to do it. So here, again, you can do it recursively, but there's not a huge advantage to doing it that way. All right, so let's move on. Next one, directory listing. This is a case where the recursion is actually a wonderfully elegant solution. So imagine if you have a directory, right? So I'm going to put this in Paint. Imagine that you have a file directory that contains both files and folders, and the folders may themselves contain files and folders. Oh, look, people are showing up. Isn't that nice? Okay, you guys can come along in. Okay, so this is an interesting problem, right? This is one, if I want to do this with a loop, there's no simple, correct way to set it up, right? Because I don't know how deeply nested the loops need to be, right? Because number one, would need one level of nesting for each possible layer of folder depth, which might change in any event. Possible layer. So that's one problem. I don't know how deeply nested the loops are going to be, right? Beyond that, it's going to take up a lot of space to code. The code itself will take up a fair amount of space, be bulky. Let's leave it that way. Will be bulky because of the multiple nested loops. And the indentations will be a problem, and it will be easy to make mistakes writing or editing the code, right? If I'm talking that there could be 20 or 30 or 50 layers deep of code, when I'm writing of the loops, when I'm writing that up in the IDE, the indentations are eventually going to be pretty significant, and that's going to be a big hassle too. So don't really want to do it with a loop. However, look at these people wandering in. Isn't that nice? All right. However, with recursion here is a wonderful and elegant solution to the problem. Okay, so if the contents of, right, so let's say as I scan through the folder, if I encounter a file, I print it. But if I encounter a folder, I send that folder to the recursive process. Okay, progress process. That is a wonderful, wonderful, and simple thing, right? So I have a method that displays all the things that are in a folder. If I see a file, then I just print it out. If I see a folder, then I send that folder to that same recursive process to print out the contents of that folder. So if in the folder within a folder I find one, I send that folder to the recursive process, and so on. Right? So give a simple example. Imagine if I have a folder that contains, right, file 1, file 2, file 3, and then folder 1, folder 2. Okay, I would first print out file 1, file 2, file 3, then print files, send folder 1 to the method, print out its contents, then likewise send folder 2 to the method, print out its contents, if folder 1 contains another folder itself, I send that folder to the method. Okay, so it's pretty easy, and it solves both of these problems. Number one, right, chop through that. Doesn't matter how deep the nesting is, as long as it doesn't blow up the stack on my machine. Second, the code itself is going to be very compact. I don't need to write this bulky, ridiculous set of loops. Instead, I can just have one method that does the trick. So we'll take a little peek in here. This is basically what the method does. So I have this method directory listing, and I accept a file. Remember that a file object can be a directory or a file. It can be a folder or a file itself. So I want to pull the list of the file. So for everything that's in this directory, everything that's in this folder, I either print it out, right? So if it turns out to be a file, I print out the contents of that file. And if it's not a file, in the else here, I call up the same directory listing with that file, which I know to be a directory, and I can go through the same process. So instead of having to do a ridiculous number of loops, you know, that takes up several pages of code, instead, I have this little simple thing that's just a few lines. It's wonderful. All right. Now, a couple other cases we can look at just as points of discussion. I don't need to get too deep into them. But here's a similar thing, right? This anagram process. So suppose I want to list up, an anagram is just a rearrangement of the letters of a word. For example, cat, any three-letter word can be anagrammed to have 6 combinations. Any three-letter word with different letters can be rearranged to have 6 combinations. So C first, it could be either A or T. A first could be either T or C. T first could be either C or A. So you can swirl that around. Now, to come up with a program that can consider all these possible anagrams, it's kind of a hassle. Again, to do with loops, you'd look at this and you'd be like, huh, how am I going to do that? Right? You have this same problem. Number one, they're going to be a lot of nested loops because you would have to do it one for each letter, right? So however long the word is, you're going to need an extra nesting of loops in there. And then there's a question, maybe you can't even figure out how to do this with loops. You look at this and you're like, huh, I ought to be able to do this with loops, but this is weird and I don't really understand how I'm gonna do that. Okay, yeah, that's loops are not a great solution for this one. So instead, the one here that we do, what it does is it breaks the word itself into a first part, a part that's already been sorted, and then a part that's been unsorted. So When I have this first word, triple letter word, right, I first do a roll through a loop, start at once with each of these 3 letters. So when I start once with C, I then send this unsorted part to that same recursive method call. And I say, okay, now do that with A, and T. So first I'm gonna sort AT and then TA. If I had 4 letters, right, say I started up with, I don't know, cats, C-A-T-S, I would first go through all the words C-A-T-S, all the letters, all the possibilities for the first letter. And then for C, I would send the remaining 3 letters to the recursion, and it would do that same swirly process with them. If you're interested in the code, right, you can look at the code here, and it pretty much works straight out of the box. You could paste this into your own browser and have it work correctly. So in fact, sure, let's do that. We have time, so why not? Just got to make sure I don't have to clean anything. Okay, so I'm going to send a prefix and a suffix. So initially, right, so the prefix is the part that's already been sorted. The suffix is the part that hasn't been. So if I send dot print line, let's see how this works. FWR dot anagram. Let's see. Yeah, let's send here nothing, and what shall we do? We shall send here code. That's a good one. What is it doing? String, string. Why doesn't it like my, oh. Oh, it's not going to return the string, okay. Just prints them out. So I'm just going to call that. Boom. Okay. So let's go ahead, we'll call that. Boom. And just like I said, first it takes this first letter and then sends the other 3 letters to the method, and then it does that same swirling, rotating process on each of them. Okay, so I get all the 24 combinations of those 4 letters. Now, if you want to look at how the method actually works, we can talk about that for a moment. So, first of all, I have a prefix. The prefix is the part that I haven't sorted yet. The suffix is the part that I have sorted. Okay, so initially the state is I haven't sorted the word at all. I haven't anagrammed it at all. So the prefix is going to be an empty string. The suffix is going to be all 4 characters. So if I reach the end, there's only 1 character left, there's only 1 possibility, I print that out. Otherwise, I rotate through the number of characters. So every character that's possible to be at that point, I'm going to run this anagramming on it. Okay, so I'm going to basically rotate around. So the new suffix is going to add in everything after the first character. The new prefix is going to be the existing prefix plus the first character of the suffix. And then I'm going to, once again, call this anagram method. I'm going to send that new substring part, right, that pair of strings, the prefix, the part that's been sorted, and the part that hasn't been sorted. I'm going to send that to get anagrammed again. And then at the end of that, I'm going to rotate the code around, rotate the word around. So the suffix will be the new suffix that I just created and the first character of it. So I'm essentially taking the first character from the suffix and moving it to the end. So I'm rotating the characters through to get all the possible anagrams. Anyway, kind of a neat thing. I don't have a compelling reason why I would need to come up with a list of anagrams for a word, but if you needed to do it, this would be a useful thing to have, right? This, again, this recursion is much, much simpler and more elegant than trying to puzzle out how you're going to do it with loops, which is not really an easy thing. So again, anagram case, it's pretty wonderful. I have another one here, the so-called Towers of Hanoi. You may have seen this as a children's game. The point of the game is to move the discs from one peg to another, but never have them with a bigger disc on top of a smaller one. So for example, if I have this case, I move the top disc to one peg, I move the second disc to the other peg, I put the small disc on top of the bigger disc. That creates a space for me to put this third disc on peg 2, I do the same thing. I take the little disk from peg 3, put it on peg 1, take the second disk from peg 3, put it on top of the third disk, and then the first one back there, right? And then I can repeat the process with the fourth disk. I put it, on the open peg then. And it can always work, right? It's once you get the process started, it's pretty easy to understand. So if I wanted to have a program that did this, again, I can't think of a particularly compelling reason why I would need to, but if I wanted to set up some code to do this, it's very short to do this in a recursive process. Regardless of how big n is, I could have a tower that's 1,000 things tall, and this is all the code I'm going to need, right? So it's very compact, again, compared to the amount of work you'd need to do with loops to achieve a similar goal. So again, the examples in the slides here, they aren't terribly compelling, except for the directory listing one. The directory listing, you'd say, yeah, that's useful and recursion is really good. That makes sense, right? These other two, it's like, yeah, okay. In a way, these are similar problems, but they're just illustrative of how much better recursion can potentially be. So if you have a problem that breaks down the same way the factorial does, where every portion of a problem is a clear component of a larger problem, then it can work pretty well, right? So in Towers of Hanoi, what we see is the set of smaller disks moving. If I add on another disk, well, that's basically a recursive call, right? I do move all the smaller disks first, and then I call again for the bigger disk to move. Likewise, for this anagramming, I first say, I'm gonna rotate all the first letters, and then rotate the later ones. So once I have C fixed in place, then I can just anagram these two. So the subsequent problems are just a component of the bigger problem. That general structure makes problems very good to attack with recursion. Okay. Similar thing happens with quicksort. Okay, so quicksort, you may recall, I introduced the other day. If we want to sort an array from some index in ascending order, the basic way we do that, we set a pivot element P. Okay, and everything that's on one side of the pivot, we put into one array. Everything that's greater than that pivot, we put into a second array. All right. Now, remember, if you were paying attention the other day when we talked about sorting algorithms, the danger of quicksort is that in this implementation of it, it picks as the pivot the lowest value. Now, if this, or the first index. So if this index is all on one side, right? If every value here is greater than or less than the pivot value, then I have a real problem, because I'm essentially going to create one more entry that goes along with each iteration through. So then it's going to be like selection sort. Every pass through the quicksort algorithm, I'm just going to put one new item in its place, and that's not going to be terribly useful. But in most cases, right, in most cases, the pivot will be somewhere in the middle like this. And then quicksort algorithm is very nice, right? So everything that's on this side of the pivot goes here. Everything that's on this side goes over here. So I make two new arrays to do that, okay? Once I've done that, I can again apply the same process. I pick a pivot value. Hopefully it's in the middle. And then I again apply quicksort to this. So I take all the values that are less than this pivot, put them in a new array, and I take all the values that are on the other side, put them in a new array. Okay, so depending on how you want to implement this, you could just have, if you want to maintain your original array in its format, you're going to need two more arrays to handle all that sorting, right? But if you're not worried about maintaining this original array, then you can just use the copy and the original as swapping back and forth. But anyway, the weakness of the quicksort algorithm, again, number one, bad, unfavorable arrangement of data, which you can have checks for that. You can implement checks for that. And number two, requires additional memory space to store the duplicate arrays. Okay, the other one, heap sort, that we did, all works within an array. All right, so quicksort, again, it is useful in some cases. If you don't mind doing the checks to make sure that you're not in one of these nightmare solutions, then situations, and yeah, quicksort is generally pretty fast, thus called quicksort. All right, and the code for it, very, very simple. I mean, you can look at this and say, oh yeah, okay, I'm gonna pick a number. If it's less than the high, you know, if whatever value in this array that I'm looking at is going to be, if it's less than the pivot, I put it in one array. If it's higher than the pivot, I put in the other. So in this case, I find as the middle, right, I have another method, partition, that I call, and I send along the array, and I send along the low value and the high value, and I try to build up new arrays with that. And I call with quicksort the half of the array, right? Everything that's in number and in the a low value, I build an array with that, and I send that to quicksort to be sorted. Everything where the values are above the pivot, I send to another quicksort method call, deal with it that way. So the code for it is very brief, and that's a nice thing. It's actually much briefer than the heap sort code itself, although the heap sort isn't too bad. But yeah, so it's quick, it's nice. And they talk about here, in the worst case, again with quicksort, if things are ordered unfavorably, it's going to be pretty awful. It's going to be like the selection sort. Even though that's unlikely, it can happen and people worry about that. But in general, yeah, it's going to be a little bit faster than heap sort. Okay. So those are some good examples. You know, again, factorial, you can use recursion on it. That's not really a compelling case, but sure, you can use it. These other three, yeah, these are really nice for recursion. Quicksort too, if you're going to do something like quicksort, recursion is a great way to implement that. However, here's one where it doesn't make a lot of sense. Fibonacci's. All right, so hopefully everybody knows what the Fibonacci sequence is. It's basically, it's where you add sequences of numbers to themselves. So if we assume that the initial numbers are 0 and 1, then we take as the next one leads to 0 plus 1 equals 1. Okay, then the next one, we take 1 plus 1, the previous two numbers, equals 2. All right, then that previous number, this 1 plus 2 equals 3, and then 2 plus 3 equals 5, and so on. Okay, so our sequence is going to look like 0 plus 1, the sum is 1, the sum of the previous two is 2, the sum of the previous two is 3, the sum of the previous two is 5, then 8, then 13, and 21, and 34, and 55, and 89, and 144. Funny how that number comes up. All right, and then what do we have next? 233, and I'll do one more, 377, and 1 more, 610, apparently, as long as I've done the math correctly. Okay, so this is one that you look at, okay, every number is going to be composed of the previous two, so maybe this makes sense as recursion. But in fact, it kind of doesn't. So you can set up a recursive algorithm for this, and it's pretty compact, but the problem is there's going to be a lot of duplicate computations. For example, to find the sum of Fibonacci of 5, you have to take the previous two numbers, 4 and 3 in the sequence. Well, to find 3, you have to do the sum of 2 and 1, and then the sum of 1 and 0, which you're also repeating down here to calculate the sum of 3 and 2. So once you find 3, you got to do these same things. Once you find 2, you have to do this. There's going to be a lot of duplicate combinations, and the higher you go in the Fibonacci sequence, the more duplication there's going to be. So again, if you're doing reasonable numbers, like around the order of, say, a few hundred, yeah, this extra computation isn't going to make that big of a difference, but it is going to be slow. It's not, the recursive algorithm is not going to be as good as a simple loop to calculate the process, right? So the non-recursive one, if I want to calculate the Fibonacci value of n, basically, first of all, I check, is it low in the sequence, and I just return 1. Otherwise, I go through and for each sequence in the computation, I add the two numbers to get the next number, right? So what I would basically do in this loop as I go through it, I first take these two to get 8, and then I remember, okay, now I need 5 and 8 to get 13, and then I need 8 and 13 to get 21, and I just overwrite what those numbers are, okay? And I just, for every number in n, I just do one computation to get to the endpoint. So if I have 100, I want to calculate Fibonacci of 100, I just do 100 of these combinations, whereas if I do it the other way, you can see that there's going to be a lot of duplication involved, and there's going to be more duplication the higher the numbers are. It's going to eventually approach something like n squared over 2. So it's going to be a lot slower, and the bigger the Fibonacci number gets, the more duplication it's going to be and the slower the process is going to be. So even though recursion is quite often useful, there are some problems that it's not well suited for. That brings us to this. This is our closing slide. General rules. Recursion is good if, number one, if the solution is natural and easy to understand, right? The case of file directory display, that's a great one. You can look at it, you say, yeah, this makes sense. Doesn't result in excessive duplicate computation, right? So Fibonacci ones, even though you can look at it and understand it, it does involve a lot of duplicate computation. It's going to get kind of slow. Or you might use recursion if the equivalent iterative solution is too complex, right? So if you've got all of those things, yeah, you have a compelling case to use recursion, right? Directory display, that's a good one. On the other hand, factorial, right? Recursive solution, sure, it's natural and easy to understand, doesn't result in excessive duplication, but the equivalent iterative solution, a simple loop to calculate factorials, is not complex at all. So you don't have a compelling case to use it. You can, but yeah. You want to avoid recursion though, number one, if you can't clearly see how the recursion process will end. If you can't just look at it and say, yes, I am sure that this is going to proceed to an end with each step, and we're going to make some progress. If you can't see that, then yeah, that's a definite red flag there, right? Or more specifically, if every call to the recursive method doesn't progress towards the end of the computations, then you risk getting trapped in some kind of infinite loop if you're not careful. Number two, if recursive solutions make overly redundant computations, sure, that's a possibility. And last, if Stack Overflow exceptions are likely to happen. So if your recursion creates so many nested method calls that eventually you get a Stack Overflow from it, you don't want to use recursion, right? Even if a loop is a little bit more complicated, yeah, the recursive way is the way to go. So remember, Stack Overflow exceptions, we can generate them very easily if we want to. Example, I could give this guy its own fun with recursion object. Okay, so if I create the constructor here, and I say this.f equals new fun with recursion, I can make it blow up. Boom, Stack Overflow error, right? Because every time I create this fun with recursion object, it has a fun with recursion object. When I call the constructor method, it creates f, but then f itself has an f. So Java tries to create f.f. Well, f.f itself has an f, so it tries to create f.f.f, and so on until the stack just can't hold all the 10,000 or so method call addresses, and the process collapses. Okay. So recursion is kind of neat sometimes. Sometimes it's very useful. Sometimes it's not much more than a bar trick. And sometimes it'll blow up your machine. So be careful with it. All right. And that's all I have to say for this lecture. If people have questions or other issues, I'm happy to stick around for a minute, but we are done.